Okay, good morning, and today we're going to do lecture 11, probability generating functions. Quick cup of coffee before we start. Okay, so let's think about it. So last time we did moment generating functions, which was a way of representing a random variable with a function that we could get moments out of. So moments, for example, the kth moment is the expected value of x to the k. So now we're going to talk about probability generating functions, which is another way of representing them. I must admit I don't use these as much. They're used more by the applied probability crew, but they're here so you can see them and we can compare them to moment generating functions. So first of all, our random variable has to take the value 0, 1, 2, 3. So basically it needs non-negative values that it takes. And what we find is that the probability generating function this time is defined as the expected value of t to the y. And this is quite nice. If you think about it, it's like a power series because you have the summation as I goes from 0 to infinity, t to the y, the probability y equals y, which is this nice form. You get 1 times the probability y equals 0, then t times the probability y equals 1, t squared, etc. And we have to choose values of t, so it's only defined values of t such that this is finite. So we'll do an example. We're going to find the probability generating function of y, where y is a geometric random variable with probability of success p. So let's do that. So what do we want? We want the p of t, which by definition is the expected value of t to the y, which will, in our case, y only goes from 1 to infinity, t to the y, and then our probability mass function, which is 1 minus p to y minus 1, and p. So we need to simplify this. It'd be really nice if in this case we could get this to be y minus 1 to agree with this one, because then we could put them together. So what I'm going to do is I'm going to take a p, bring it out the front, take a t, bring it out the front, and simplify. So we're going to have our p t, summation y equals 1 to infinity. Now we've got t to the y minus 1, 1 minus p to the y minus 1. So we can put all that as p to the t, y equals 1 to infinity, t 1 minus p to y minus 1. Now what we've got here is got something that looks like a power series, or geometric series. We'd like to simplify this. So I'm just going to go let x equal y minus 1. So now we've got pt. When we have y equals 1, then x would equal 0. And when y equals infinity, x is still infinity, because infinity minus 1 is still infinity. We've got t to the y, 1 minus p to the x. And that's a geometric series, so we can write that as pt over 1 minus t, 1 minus p, provided that t, 1 minus p is less than 1. Cool. So what sort of properties do we have? Well, first of all, if you put the value t equals 1, you'll get the probability of that is 1. If you put t equals 0, you get the probability y equals 0. And if you take your probability generating function, you differentiate it k times, and then put t equal to 0, you get k factorial py equals k. So as you can see, it's a way of getting probabilities, hence its name, a probability generating function. And if you differentiate k times but t equals 1, you get the expected value of y, y minus 1, y minus 2, etc. And obviously the expected value of y, y minus 1, we've seen a lot before. We've used it quite a few times to get variances, so that's going to be useful. Let's just check. We'll check the first two, make sure we see where these come from. So first of all, let's look at p of 1. What is that? That's the expected value of 1 the y, which is, well, in general case would be y equals 0 to infinity. 1 to the y, the probability y equals y. Which, well, 1 to the y, whatever it is just going to be 1. So this is y equals 0 to infinity. The probability y equals y, which is 1, because this we are using the old sum over PMF. And it's a valid PMF. What about P0? Well, that is, well, remember that nice form we had? It's the probability y equals 0 plus t, which is 0, the probability that y equals 1, plus 0 squared, the probability y equals 2. So basically, every term that has a t in that sum has a 0 now, so it disappears. In fact, the only one that doesn't is the probability y equals 0. Cool. So let's do another example. We'll do the Poisson random variable one, and then after that we'll use that to find the expected value and variance like before. Okay, so let's first of all do this. So we're going to do a Poisson. So we've got P of t equals, again, the expected value of t to the y. So we're going to sum, as y goes from 0 to infinity, our function, which is t of y, times our probability mass function, which is e to the minus lambda, lambda to the y over y factorial. So we're going to use a trick we did before. What we're going to do is, first of all, we're going to bring out any terms that are constant with respect to y. So the main term that's constant with respect to y is this. This one's got y, this one's got y, this one's got y, so we can't bring them out. So let's do that. We'll go e to the minus lambda, y equals 0 to infinity. And what we've got left, we've got a lambda t to the y, so put the two terms together over y factorial. And again, what you should do now is you should recognize this as the Taylor series of an exponential. So what is this? This is e to the minus lambda, and then we've got e to the lambda t. Let me just check that with my notes. Yep. So that is our probability generating function for Poisson. Okay. Well, let's use them to get the expected value of y and the variance of y. Well, how we do the expected value? Well, there's a couple of ways we do it, but the way we're going to do is we're going to differentiate it, our probability generating function, for respect to t. So if we do that, we should get, and I'll say, go and try it yourself, e to the minus lambda, lambda to the e lambda t. What happened there? Well, it looks very complicated, but the only real term in this whole thing here, so if we go back here, this is what we're going to differentiate, and we're differentiate with respect to t. So this is the only term we really care about. As far as we're concerned, this is a constant. And if I have e to the lambda t and I differentiate it, basically use the chain rule. So you write it again, e to the lambda t, and then you take your lambda t, you differentiate that with respect to t, and you just get lambda. So that's what we did here. Now we will set t equals 1. So I get e to the minus lambda, lambda, e to the lambda. And remember, this is going to be lambda e to the lambda minus lambda, because when you multiply, you add the superscripts. So that is basically 0, and e to the 0 is 1, so we get lambda. Okay, next, we're going to differentiate our probability generating function twice. Well, we've already done it once, let's do it again. By the same process before, we'll get e to the minus lambda, lambda squared, e to the lambda t, and we'll set t equals 1. If you do that, you get lambda squared. But what is this? If you go back and look at the properties, that will be the expected value of y minus 1. So now we need the variance to put it all together. The variance of y equals the expected value of y minus 1. If you expanded that out, that would be the expected value of y squared minus y. So if I add an expected value of y and I minus the expected value of y all squared, that will give me my variance, because the variance is the expected value of y squared minus the expected value of y all squared. Substitute in, you've got a lambda squared plus lambda minus lambda squared, which equals lambda. Same as we got before. Cool. So that's probability generating functions. All we've got to do now for this chapter is to finish off our motivating example. I'll record a separate video for that. Have a go at it in the meantime, and I will put that up soon. Thank you very much.